Hello, students, and welcome to the review for Unit 1 of Algebra 1B. This is the second semester of Algebra 1, and it contained a lot of information, a lot of topics and skills that you're required to use in the following units in the course. I am not going to talk about everything you learned in this unit, but I'm mainly focusing on those things you need to know for the test. But even so, that's quite a bit, so let's get started. First of all, there was a lot of vocabulary to learn in this unit, and we learned about different kinds of polynomials, the terms within polynomials, and what their names are. Now, terms, not complicated, they're just chunks of an expression that are separated by plus and minus signs. So, poly, the word poly means many. Polynomial can have many terms, and some have specific names. A monomial has one term because mono means one. So x or 5x squared y are both monomials. Notice that 5x squared y has a lot of different factors, but they're not different terms because there are no plus or minus signs. A binomial, on the other hand, has two terms, so there has to be a plus or a minus sign separating the two terms. A trinomial, obviously, has three terms. Here's an example, x plus y minus 7, or x squared plus 4x minus 15. You should be able to count how many terms a polynomial has and remember the name for it up until this point. Beyond that point, they're just called n-gons or 7-gons, something like that. Let's continue. The only thing that we're worried about when we simplify expressions are the like terms. Like terms have the exact same variables, except for the number portion or the coefficient. So here's some examples of what are and are not like terms. X and y are not like terms because you can see they're both variables and they are not the same. 5x and 7x, however, are like terms because they both have a single x factor. Ignore the 5 and the 7, you're just looking at the variables. What about 3xy squared z and 3xyz? They both have x, y, and z, but notice that the y is squared in the first term and not in the second. So they are not like terms and cannot be combined. When you add or subtract like terms, once you find out that the variables are matching, you simply add or subtract the number portion or the coefficients. So 5x plus 7x equals 12x. It's kind of like you're picking up x's off the ground. 5x's plus 7 more x's are 12 x's in all. Don't get this confused with multiplying different factors where you would end up with x squared by multiplying. We're simply adding the numbers of x's. And subtraction works the same way. Remember that a term without a coefficient has a coefficient of 1. So if I'm adding 5x plus x, that's 1x. So 5x plus 1 more x would be 6x. And subtracting would be the same. If the terms are the same, 5x minus 5x equals 0, just like any other two numbers that are equal, subtract the big 0. Remember, you can only combine like terms. So in this expression, x squared plus 5x plus 7x plus 8, only those two middle terms can be combined, the 5x and the 7x. So the simplified expression would be x squared plus 12x plus 8. The x squared and the 8 do not change. You can also add and subtract complete polynomials. So here is a sample question that you might see on your test. 5x cubed plus 4x squared minus 7 plus negative x cubed plus 8x minus 9. Now, when you are adding, there's nothing different than just sticking these two things together and finding the like terms, just like we've been doing. So 5x cubed minus the x cubed from the other polynomial makes 4x cubed. 4x squared plus 8x don't match, so they're going to come over as is, plus 4x squared plus 8x. However, the numbers are combined because they don't have a variable at all. So minus 7 and minus 9 make minus 16. So to add these two polynomials together, all we did was combine like terms. Now, of course, subtraction is not that easy. You might see a problem like this: 5d squared plus 4d minus 3 less 2d squared minus 3d plus 4. Like all problems with subtraction, order is important. When you're subtracting the second polynomial, that means you have to subtract each of these terms individually. There are a couple of different ways to write this, but I've chosen to change the signs of each of these numbers as I add it to the first one. So here's my first expression, 5d squared plus 4d minus 3. Now instead of positive 2d squared, I put minus 2d squared. Instead of minus 3d, I put plus 3d. Instead of plus 4, I put minus 4. In other words, I'm subtracting each term. Remember, subtracting is just adding the opposite. Now I can go back and rearrange and combine like terms. There's a 5d squared and a minus 2d squared, resulting in 3d squared. There's a 4d that matches with a 3d. Together they make 7d. And for the numbers, minus 3, minus 4 make minus 7. Now, you did quite a few of these in your practice problems, but they still might be confusing. And if they are, let me know and I can provide some additional examples. Now, sometimes you're subtracting a negative. And just like when you learned about negative numbers, subtracting a negative makes a positive. So here's an expression, 3z to the 7th minus negative 5z to the 7th. They're like terms and I want to combine them, but there's a minus minus. I can combine those to create a plus problem. Negative 3z to the 7th plus 5z set to the 7th would be 2z to the 7th. Use the same techniques working with negative polynomials. Okay, so we're going to take 5d squared plus 4d minus 3 less 2d squared minus 3d plus 4. Same problem we had before, but this time I'm going to change the signs of each of the terms in the polynomial, combine them, and I come up with the exact same answer, 3d squared plus d. Now, this gets super complicated when you've got embedded groups. You might have parentheses inside brackets, inside braces. And if they have a minus sign in front of them, that means you're going to have to go through and change the signs of each of the terms in the polynomial being subtracted. Starting from the inside out, in this example, m plus n minus p are in the inside set of parentheses, and they have a minus sign in front of them. To get rid of those parentheses, I have to change it to minus m minus n plus p. I change the signs of each of the three terms, allowing me to remove the parentheses. I left the initial p in that bracket because it was not being subtracted. I can go ahead and simplify whatever is in this bracket now, and the only two like terms are the two p's, so I can rewrite it as m minus brace n plus 2p minus m minus n in those brackets. Now, in front of the brackets, there's a plus sign. That means I don't need those brackets at all. I can just simply remove them. I don't need to change the signs. So I'm going to rewrite it as m minus brace n plus 2p minus m minus n. Notice there are two n terms in here that can be combined. Positive n minus n. That's going to result in 0, so no n's will appear in the simplified form. Now I simply have m minus brace 2p minus m, and I'm going to change the signs of the terms inside the bracket, or inside the braces, because they follow a subtraction sign. So here, instead of 2p, I have minus 2p, and instead of minus m, I have plus m. The braces disappear and allow me to combine the two like terms, which are m and another m, resulting in 2m minus 2p. Now, if I went through this too fast for you, you're welcome to back up this video, watch it again, or let me know and I can provide you with a different example, or we can meet in my classroom and go over some others together. Multiplying monomials is kind of like multiplying plain old numbers. If you have x cubed y squared and you want to multiply it by 4xy cubed, again, you're kind of looking for the same variables, but in this case, we're multiplying. If each of these factors are multiplied together, the exponents become larger. So x to the third power times x to no power, or just the power of 1, is going to increase to x to the fourth power because there are now 4 powers of x. Notice I kind of skipped over this 4. 4 doesn't have any other number to multiply with it, so that is going to be unchanged. I'm going to move over to the y section. I've got a y squared, meaning 2 factors of y, multiplying by y cubed, or 3 factors of y, give me 5 factors of y altogether. Remember, the rule of multiplying powers is that if the base is the same, you can add the exponents when you multiply. So the final product of this is the 4 that remained unchanged, the x to the fourth, and y to the fifth. Now, when it comes to multiplying a monomial by a longer or larger polynomial, you're going to use something that looks exactly like the distributive property you've used all along. The number or term on the outside is going to be multiplied by each of the individual terms inside the parentheses in order to complete the distribution. So breaking this up, I've got negative 4x cubed times 4x squared, then my plus sign, negative 4x cubed times 3x, the second term, then my minus sign, then negative 4x cubed times 14, the last term. Okay, let's practice what we did on the last slide. This time I have 2 numbers, negative 4 and 4 multiplied to get negative 16. X cubed times x squared make 5 factors of x, so negative 16x to the fifth is the first new term. Negative 4 times 3 is negative 12. X to the third power times x to the 1 power is x to the fourth power. There are 4 factors of x. Here we come up with a minus minus again, and as we talked about before, that makes a plus, so there's my plus sign. Then I have a positive 4 times positive 14 for positive 56, and x cubed has nothing to multiply by, so it comes down as is. The completed product then is negative 16x to the fifth minus 12x to the fourth plus 56x cubed. Now, sometimes you have 2 polynomials that have to multiply by each other. The easiest way to think this through is that you're going to take each one of the factors from one polynomial, or the terms from one polynomial, and multiply it, like we just did in the last slide, by both of the terms in the second polynomial. So here I'm taking 2a squared first, and I'm going to multiply it by a minus 1. First by the a to get 2a cubed, then the minus sign, then by the 1 to get 2a squared. Done. Then I'm going to go back and get my 5a and multiply it by a minus 1. 5a times a is 5a squared. 5a times negative 1 is negative 5a. Done with the second term. Then I'll take my third, negative 7, and multiply it by a minus 1. Negative 7 times a is negative 7a, and negative 7 times negative 1 is positive 7. Now I'm going to collect them all and put them in order, in descending orders of the exponents of a, so that I can combine any like terms. There's no match for the a cubed, so that comes straight down as is. But there are 2 a squared terms, negative 2a squared plus 5a squared, resulting in 3a squared. There are 2 a terms, minus 5 and minus 7, resulting in minus 12a. And finally, there's just one number, and it will come down as is since it does not combine with any other terms. FOIL is a special method that we use to multiply 2 binomials. It really isn't any different than the process that I just showed you, but because this is the most common way that we multiply, there's sort of a shortcut. FOIL stands for first, outside, inside, and last. And that has to do with the order in which we multiply the two binomials together. So the process is to write them side by side in their respective parentheses, determine which ones are the first terms, which ones are the inside terms, and which are outside. So first terms are x in one polynomial and x in the other. X times x becomes x squared. Now to the outside terms. X times negative 2 is negative 2x. Now to the inside terms. 8 times x is 8x. And finally, for the last terms, 8 times negative 2 is negative 16. Notice that the middle two terms both have an x, so they can be combined. Negative 2x plus 8x becomes 6x, and the other terms come down unchanged because they didn't have anything to combine with. So the final product is x squared plus 6x minus 16. This is a good skill to practice. Once you practice it, it'll become like easy peasy. Now, dividing monomials is very similar to multiplying, except the rule is if you have two bases that are the same, you will subtract the factors, or subtract the exponent, sorry. Let's see why that works. I have x to the fourth, and that means I'm multiplying x times x times x times x. And I'm going to divide it by x to the third power, which is x times x times x. Now, if you remember how fractions can be reduced, anything that matches on the top and the bottom will cancel out. So 1x and 1x cancel, another x and another x cancel, another x and another x cancel, leaving me with just one remaining x on the top, which equals x. So what I've done is taken x to the fourth divided by x to the third and subtracting the number of x's I had by the other number of x's I had and ending up with simply x. My original problem here is 12x to the fourth y squared divided by negative 3x cubed y. First of all, you would look at the numbers. 12 divided by negative 3 becomes negative 4. Then we've already looked at the x's. X to the fourth divided by x cubed would equal simply x. And then we go back and look at the y's. Y squared divided by y equals y. Now remember, if there's no exponent on a variable, it has an exponent of 1. So 2 minus 1 is 1, and that becomes simply y. So the final quotient is negative 4xy. Now, sometimes you have a larger polynomial and you want to divide it by a monomial. So you just do the same thing we just did, but you do it step by step with each term in the polynomial. So starting with the 3xy, we're going to divide it by 3y. 3 divided by 3 becomes 1, so you don't need to write it. X divided by nothing to divide by, so it comes straight over as is. And then y divided by y becomes 1 as well, so 3xy divided by 3y is simply x. The next term is negative 12y squared. Negative 12y squared divided by 3y would start with negative 12 divided by 3 for negative 4, and y squared divided by y would give you y. The next term is 15yz. 15 divided by 3 would be 5. Y divided by y would be 1, so it's not written at all. And the z is not divided by anything, so it comes straight over. Now you can collect these three different terms. X minus 4y plus 5z is the final quotient. One way that makes it easy to divide by a monomial, or knowing what to divide by, is to find the GCF, or the greatest common factor. Now, you've learned in previous years about how to do this with numbers. 15 only has factors of 1, 3, 5, and 15. Negative 18 has factors of 1, 2, 3, 6, 9, etc. It has a lot. We only have to check for the 5 and 3 because dividing by 1 won't get us anywhere. 15 is obviously not a factor of 18. 5 is not a factor, but 3 is. So 3 is the greatest common factor of 15 and negative 18. Now, that's the hard part. The easy part is the variables. If you're trying to find the GCF of a squared and a cubed, it's a squared. You always choose the variable that has the lowest exponent because obviously it's a factor of a cubed, but a cubed could never be a factor of a squared because it's larger. Try it again on the b's. We've got b cubed and b. B to the 1 power is the lowest one, so the greatest common factor is b. And there's no common factor for c's because it only occurs in one of the terms. So the GCF of this problem is 3a squared b. Both of these terms, or both of these monomials, can be divided evenly by 3a squared b. Factoring trinomials is another one of those skills that once you develop it, it will come in very handy and it'll get faster and faster. It looks a little bit like guess and check, but there really is a method to it. And it starts out like this. Let's say that you have a trinomial, x squared plus 13x plus 12. The first thing you would do is look at all the terms and see if there's a GCF. But here there's nothing I can divide all three of them by. In that case, I'm going to start by looking for binomials that might multiply together to create this trinomial. And I always start out with two sets of parentheses. And in this case, because the first term is x squared, and remember, I know that the first term of my product is going to be the first terms of the two binomials. So I'm going to take the factors of x squared and put them in the first position in my two binomials. X times x is x squared. Now, this comes the tricky part. I'm looking for some numbers to go in the rest of the binomial, but they have to fill a certain pattern. I'm looking for two factors that will multiply to 12, but they have to add to 13. Okay, let's see if we can find out some options. Well, 3 times 4 equals 12, but 3 plus 4 is 7, not 13. 2 times 6 is 12, but 2 plus 6 is 8, not 13. 1 times 12 is 12, and 1 plus 12 is 13, so those are the numbers I'm going to choose. Since everything is plus in this polynomial, it doesn't matter which order I put them in, so I end up with x plus 1 times x plus 12. Now, that seems like it works because I chose the numbers specifically to go back to my original trinomial, but let's check it with FOIL. F would do x times x equals x squared. O is x times 12, or 12x. I, inside terms, is 1 times x, or x. And last is 1 times 12, or 12. Collect all the terms, 12x plus x plus 12 equals x squared plus 13x plus 12, and it checks out. Dividing these polynomials by factoring the first polynomial, then comparing the factors to the divisor. Now, this doesn't always work, but in this case it will, and this problem is one from your test. I've got a trinomial 6x squared minus x minus 40. Some factors of 6x squared are x and 6x, or 2x and 3x. So I'm going to start two sets of binomials with those two, and I don't know which one's going to work, so I set up two of them. I've got one with 6x and x, and one with 2x and 3x. Some factors of negative 40 are negative 1 and 40, or negative 2 and 20, or negative 4 and 10, negative 5 and 8. Oh my goodness, there's so many. So I could also switch those around to make them 1 and negative 40, or 2 and negative 20. So I'm just going to try some of these out into these in a little guess and check way. By trial and error, I'm going to end up with 5 and negative 8. Because when I combine it with my 2x and 3x, 2x times 3x is 6x. My outside terms are negative 8 times 2, which is negative 16. Adding that to my inside terms of 15 results in negative x. And then finally, my 5 times my negative 8 is negative 40. So if I compare the factors to the divisor, 5 plus 2x, and my divisor right here is what I wanted to originally divide it by, I have a 2x plus 5 as one of my binomial factors of the trinomial. When two terms are added, it doesn't matter what order they're in, so these are matching binomials. And so I can actually cancel those out when I divide this polynomial, knowing that 2x plus 5 was a factor. I can divide that part out, leaving me with just the second binomial as 3x minus 8. So in this case, it worked out. It doesn't always work out, but that's one method that you can choose if you have to divide a trinomial by a binomial. Another method you can use is long division. This may seem tedious, but it can be used with any size polynomials. And here's how it works. I think you have one problem on your test where you actually have to write this out. So you might want to write this down on your paper so you have it handy. I'm dividing y to the fourth plus 0x cubed. Now notice that the original problem was a to the fourth plus 7. Why do I have a 0x cubed? Well, because like a number under a division sign, you have to have a hundreds column, a tens column, a ones column, etc. I didn't have any x cubed column, but I do have a 2x squared. I have a 0x because there was no x in the original, and a 7. So it looks like I might have made a mistake. It looks like I'm trying to divide a to the fourth plus 2x squared plus 7 by a minus 3. So let's give it a try. Here's the way you think it through. I know that this a in my binomial divisor has to multiply by something to become a to the fourth power. That means I need 3 more powers of a. So I'm going to multiply by a cubed. And because it's in the a cubed column, I'm going to put it right here. Multiplying a cubed by a plus 3, that's at 3, a minus 3. A cubed times a is a to the fourth. A cubed times minus 3 is minus 3a cubed. So I'm going to write this into my problem so that I can subtract a to the fourth. And remember, that's always going to match because that's why I chose that number. Minus 3x cubed. Subtracting just those two terms, the first two become 0. 0x to the cubed minus negative 3x cubed is positive 3x cubed, because remember, subtracting a negative becomes a positive. So that's a positive number. And then I'm going to bring down my next term just like you would if you were doing long division with numbers. And I'm going to go back and ask myself, how many times does a go into 3x cubed? Well, I'm going to have the number, that's a 3, and I need 2 more factors of a. Wait a minute. See what I did here? I made a mistake. These should be a's, right? I just wrote the problem wrong. It's not going to change the way it comes out, but for some reason I put x's in here instead of a's. Okay, so multiplying 3x squared, or a squared, sorry, is going to get the result that I want. And because 3 is positive, I want that to be plus. Okay, now 3a squared times a minus 3 is 3a to the third minus 9a. Okay, and I'm going to subtract that. 3a cubed, we'll just remember, we'll kind of ignore that x up there, minus 9a squared, no, 9a. Oh, 9a squared squared because we multiplied 3a squared times negative 3. Subtracting, I get 0 for the first terms, and 2a squared minus negative 9a squared gives me plus 11a squared. Okay, now I'm going to do it again. A goes into 11a squared 11 times, and I need another factor of a. It's going to be positive again. And then I forgot to bring down my 0a, but it's going to be sitting right here, and it doesn't have any value, but if I have to subtract from it, I need it to be there. All right, now 11a times a minus 3, and I'm kind of running out of space, so I'm just going to put this straight over. 11a times a is 11a squared. And 11a times negative 3 is negative 33a. Okay, subtracting, the first two turn out to be 0. Then 0 minus negative 33 becomes positive 33a. And I bring down that 7. Now, what do I multiply a by to get 33a? I multiply it by 33. 33 times a is 33a. And 33 times negative 3 is negative 99. Well, the first column turns out to be 0, but 7 minus negative 99 becomes positive 106. So I have a remainder of 106. So long division is just like long division was with numbers. It just becomes a little bit more complex because you have to remember everything about dividing and multiplying complex polynomials. If you need another example, there are a couple in your in your lesson that you can go back to, and you're welcome to come into my classroom and see a few on your own. Okay, for the last few minutes, we're going to just practice factoring a trinomial. And remember I said the more you practice, the better. So just let me talk you through it. Put your first two sets of brackets and figure out what you're going to divide your p squared by. And the only factors it has are p and p, so we're going to start there. Now here's a hint I didn't talk about before. If the last number is negative, that means one of your binomials will have a plus sign and one will have a minus sign, because the only way to get a negative product is to multiply a positive and a negative factor together. Now I'm looking for numbers that multiply to 20 and subtract to become 8. So factors of 20 are 1 and 20, 2 and 10, and I'm just going to stop right there because I think if I subtracted 2 and 10, I would get negative 8. Now I'm going to get negative 8 only if the 10 is negative. So I'm going to put my 10 over here and my 2 over here, and I'm going to check it out. Okay, first terms, p times p is p squared. Outside terms, p times negative 10 is negative 10p. Inside terms, 2 times p is plus 2p. And 2 times negative 10 for my last terms makes negative 20. The middle terms almost always combine, and here we've got minus p plus 2, so that's indeed minus 8p. And this checks out to be the same trinomial we started with. So there you go. Now let's try one that's a little bit trickier. I've got my two binomials set up, but notice that this time there is a coefficient in front of the x squared. So I know I'm going to have an x here and an x here, but I've got some options. This could become 1x x and 6x or 2x and 3x? So I'm going to start with my 2x and 3x and just see if I can get it to work out. If not, I'll switch and make another set with 1x and 2x. Because the last number is positive, I know that both of my signs will be the same, but the middle one is minus, so both of these are going to have a minus sign. Now I'm looking for factors of 5. Well, luckily the only choices I have are 5 and 1. But I don't know which one is going to take the 5 and which one's going to take the 1. So let me just put some in and do a little guessing and checking. I know that my first term will end up being 6x squared, and I know my final term will be positive 5. So all I really need to do is check out these middle terms. The outside will be negative 2x, and the inside will be negative 15x. And as you can see, negative 2 and negative 15 do add to negative 17x. So my first guesses were correct. But if your first guess isn't correct, don't get discouraged. Just try the other options until you find one that checks out. There are some special circumstances where you can take a little bit of a shortcut. Here we have a binomial, but it doesn't have any b term in the middle, otherwise it would be a trinomial. Because the b is squared, I know this can be factored into 2 binomials. But this special polynomial has a specific feature. It is called the difference, meaning the 2 terms are subtracted, of 2 perfect squares. In order to be a perfect square, the number portion, such as 9 and 4, have to be perfect squares. 9 is 3 squared and 4 is 2 squared. And the variable has to be a perfect square. B squared can be divided into b and b. So the only thing I have to do here is to remember the little shortcut. I'm going to take the square root of each of the terms from my numbers. So that means 3b and 2. I'm going to put the identical terms into both binomials. And here's the thing you have to remember. 1 will be plus and 1 will be minus. And I'll show you how this works out. First terms, 3b times 3b are 9b squared. Outside terms, 3b and negative 2 are negative 2b. And because they're nearly identical, 3 times negative 2 is not negative 2, it's negative 6. Okay, my inside terms, 2 times 3b become positive 6b. And finally, my last terms, 2 times negative 2 become negative 4. The 2 middle terms cancel each other out. I've got a negative 6b plus positive 6b, so they become 0. So my only remaining terms are the 6b squared and the minus 4. Because of this, you know that you can factor this into 2 identical binomials, except for the fact that one will have a plus sign and one will have a minus sign. There's another method for factoring that's called factoring by grouping. This is most often used when you have 4 terms or a 4-term trinomial or 4-term polynomial. What you have to do is, and again, there's a little bit of guess and check, but you can rearrange the terms so that you know that each set will have a common factor. So here I've chosen PQ and PR to be together at the beginning, and negative 3R and negative 3Q in the end, because the 2 sets have common factors. Then I'm going to sort of split them up right here. And I'm going to take the P out of the first 2 terms, putting it outside parentheses and leaving the Q plus R inside. Then I have my minus sign. Minus 3 is a common factor for both of these. And if I divide it out of these 2 terms, I'm left with Q plus R inside. Notice that the Q plus R is now a common factor of both of these terms. So I can pull that to one side and put the leftovers in another set of parentheses, p from here minus 3 from here. Now this is very complex, and it's going to take a few times through factoring by grouping to kind of get it. But once you do, and you see the sign that you're going to have a 4-term polynomial, then that's kind of your signal that you want to give that factoring by grouping a chance. Okay, we're almost done here. Make sure when you factor that you are doing a complete factorization. Sometimes that means that you have to look at the factors first to decide if there's any common factor. It might be a variable or it might be a number. In this one, I've got 3x squared minus 15x minus 42, and you might notice that each one of these number portions or the coefficients is divisible by 3. So I can immediately pull 3 out to the outside and leave the remainders inside. 3x squared divided by 3 is x squared. Negative 15x divided by 3 is negative 5x, and negative 42 divided by 3 is negative 14. Now I can reverse FOIL, or basically factor, and it's much, much easier because there's no coefficient in front of the x. So I've got my x and my x for my first terms. Then I'm looking for 2 factors of negative 14 that will add to negative 5. And I chose positive 2 and negative 7. Or subtract the negative 5. And if you needed to check this out, x times x is x squared. The outside terms are negative 7x. The inside terms are 2x. And the last terms are negative 14. I can combine the middle 2 terms to get negative 5x. Then I can go back and multiply each of these terms by 3 to get back to my original polynomial. 3x squared minus 15x minus 42. All right. The biggest thing you need to look for when you're trying to factor completely is finding that GCF. Here's a more complex one. I've got a 360t, a 10t cubed, and a 120t squared. Well, I can immediately see they all have a t, but it's a little confusing the way that they've written this because they've got the t first, the t cubed second. So I'm going to reorder this in descending order, not changing any numbers. 10t cubed minus 120t squared plus 360t. And I can see immediately that all the numbers are divisible by 10. In fact, that's the greatest common factor. So I can divide out a 10 and a t from each of these terms. When I do, I put the 10t on the outside and the remainders on the inside. 10t times t squared would be 10t cubed. 10t times negative 12t would make negative 120t squared, and 10t times 36 would make 360t. Then, if possible, I can continue factoring. This t squared minus 12t plus 36 divides up into t minus 6 times t minus 6. So my completely factored polynomial is 10t times t minus 6 times t minus 6. Here's a really long polynomial that might look like you can't possibly factor it, but I'm going to try grouping and then rearranging things to see what I come up with. I can immediately see there's an x to the fourth, x squared, and y squared, so I don't have an x squared in every term, but I could take it out of the first 2 terms. So looking at just these first 2, I would take the x squared out, leaving behind x squared minus 9. Then looking at the second 2, they both have a y squared. I can take that out and leave the remainders inside, which also end up being x squared minus 9. Now I know that I can put my common factor, x squared minus 9, and the remainders, x squared minus y squared, into a separate binomial. Both of these happen to be the difference of two squares, so they will result in identical binomials, except one will be plus and one will be minus, using the square roots of each of the terms. X plus y times x minus y is the same as x squared minus y squared, and x plus 3 times x minus 3 is the same as x squared minus 9. So this has been factored completely. That last one looked pretty complex, and if you have a question about it or about anything else that you saw in this presentation, please let me know when you call. If you're good to go, you may go ahead and submit this assignment and open up the test. If you would like to see more examples of any of these, you're welcome to go back into your lessons and check, or you're welcome to give me a call, like I said, or send me a note or say, you know what, I need help. I think I need to do a private review session before I take this test. There is a lot of information in here, and I'm sorry that this review is so long, but I wanted to make sure you had a thorough review before you attempt the test. So give me a call to get credit, and good luck on the test.